Hello. Today we are going to start learning about electrical energy. Here is your I can statement for the last part of this unit. It is that you should be able to explain how electrical energy is transferred in a complete circuit. Now, before we start talking about circuits, we need to understand a little bit just about electric charges, electric force, and static electricity. Then we'll get into talking about current electricity and circuits. So I'm going to show a little bit, I just want to kind of show you what you're going to be doing on your notes. You have a diagram at the top of your notes, and notice that the title of these are the atom and the ion. And we've learned a lot about the atom and a little bit about the ion thus far. So we're going to take a minute to kind of recap on those. So on this diagram that we're looking at, you'll see that there are some subparticles that are located in the middle of the atom, which is the nucleus. And the ones that have a plus sign in your diagram, there's two of them, are called protons. So go ahead and label those. And the ones that have no charge are called neutrons. Now, outside of the nucleus, you'll see on your diagram, you only have one energy level. And the electrons on your diagram are colored in dark. And I would like you to also label those electron. So just recapping on those are the three subatomic particles and their charges. Most atoms, and this is below your diagram, we learned have a overall neutral charge. And that is because they have an equal number of protons and electrons. However, sometimes atoms do have an unequal amount of electrons and protons. So they might have more electrons than protons and have a negative overall charge, or they might have more protons than electrons and have a more positive overall charge. This type of atom is called an ion. Make sure that you have all those filled in at the top of your notes above where it says the second title, electric force. Okay, so if an atom or any object has an electric charge, that means that it either is positively or negatively charged. And as you guys know, in working with magnets in the past, when you have two like charged items, maybe two magnets that the positive or the north poles are facing each other, that is going to push away from each other. But when you have opposite sides of magnets, just like if we had two atoms, with one a positive charge and one with a negative charge, both being actual ions, then they would pull on each other and pull closer to one another. So that's what we mean by electric force, just that two items came close to each other and they are either pushing and pulling each other because they have like charges or opposite charges. All right, now it's important to understand that since the electrons are located on the outside of the nucleus, and therefore they are not held in as tightly, and they also have much less mass than protons, they will be the ones to move due to this pulling and pushing force that's being created between two particles with charges. All right, so next we're going to talk about how this electric force sets up an electric field. So basically, an electric field is just a region or an area around a charged object. And it can be an indirect force, which means that two items do not have to be touching each other for there to be pushing and pulling going on between them, as you probably know with magnets. All right, so let's look at this example with a balloon. So here you have a young lady who is holding a balloon, and if you notice, the balloon has a few positively charged particles and a couple negative charged particles. And at that point, it is not attracting the girl's hair. Now, once she rubs the balloon on her sweater, more electrons are going to move onto the balloon. And that has to do, and we're going to get into this, but that has to do with the material that both the balloon and the sweatshirt or sweater are made up of. But in this case, the negative charges from her sweater are going to move to the balloon. And then the balloon will have many more negative charges than positives. So as that same balloon is held up to the hair now, the negative charges will attract all of the positive charges in the girl's hair, and that is why her hair will stick to the balloon. Now, this is a list, and it's called the triboelectric series, and it is a list of materials in the order of how easily they give off electrons. So your hand gives off electrons fairly well. I'm sure that you have gotten kind of like a static shock once in a while when you go to touch a doorknob or touch a person. At times, you will get a short burst of electrical force. And we'll talk about static electricity in just a second. But at the bottom, you'll see things like polyester or polyvinyl chloride plastic, which is just PVC plastic. And then those things in the middle, wool, fur, silk, those things kind of do an okay job of releasing their electrons. Moving on with static electricity, it is important that you know that this is different from current electricity. Static electricity is a short burst of electrons from one object to another. So it's not a flow of electrons that keeps going and keeps going. It is very quick and over with. Now, if you kind of watch this simulation for a few seconds, you'll notice that as this guy is walking, he is leaving electrons along the ground because the friction between his soles of a shoe and the ground that he is walking on is allowing those electrons to leave the soles of a shoe and enter to the ground. Because he now has a more positive charge, when he goes to reach for that door, all those negatives in that door quickly burst to his body. And I'm sure you've felt this before, but it's a quick burst called static electricity. All right, so next we're going to get into current versus static. And current, if you can't already tell, means that it will be a continuous flow of electrical charges through a material. So this is where we conducted a short experiment earlier in the year where you created just a basic circuit, and it was the insides of a flashlight. And so we're going to be getting into a little bit more complex circuit building in the next few days. Now, for whatever reason, I am not really able to view. Let me see if I can view these. Okay, good. So by now, you should have most of the front page of your notes filled in, or first page of your notes. There's a few questions in the true and false section that you haven't quite been able to answer, but we will get to that. So while we're answering both those bottom 2 or 3 questions, we will also be filling in the chart that is at the top of the second page. So stay with me here. All right, so moving on in the presentation, how is a current measured? It's important to know that electric current is defined as the amount of charge that flows past a point at any given time. Therefore, the higher the electric current, that just tells you that there are more charges flowing through the wire. And this current is measured in amperes, and its symbol is actually a capital A, so make sure that you get that in your notes. But the abbreviation for it is AMP, and I'm sure you've heard of that abbreviation. So you have the name, you have the short abbreviation for it, and then when we write it just as a symbol, it's a capital letter A. So here, this is just a different way of thinking about current. We have tomatoes on a conveyor belt, and they're on a confined path. So that's kind of similar to how electrons flow, because if we're talking about a circuit, we're usually talking about a piece of metal wire that is connected. And so electrons are flowing along that metal wire, just like these tomatoes are on the conveyor belt. And if the tomatoes move faster, then that means that more tomatoes are passing by the worker every second. And therefore, in relation to electric current, if we had more electrons flowing past a certain point, that means that there is a greater current. So the amps would be higher. All right, voltage. As far as description or definition, it is the force that makes electricity flow. And you're going to be reading a little bit more about these vocabulary terms. All right. So you're going to be reading about these in your book, so it will help you understand. But this is the force that makes electricity flow. And voltage relies on a source of energy. So in the circuits we're going to be putting together, it is a battery. It could also be a generator. But you have some kind of source of energy or power to get those electrons flowing. And it is measured in volts, and that is with a capital V when it is used as a unit. Okay, so we have two types of materials, and you've heard of these before. Insulators, but you need to know also those are called resistors, and conductors. So insulators or resistors are materials that electricity does not flow easily through. So if we go back to talking about that triboelectric series list that we looked at earlier, and that's just a short version of that list, you would see these items being at the bottom of that. And they are usually nonmetals and some metalloids, or just some mixtures of things with nonmetals and metalloids in them. Now, there are also conductors, and conductors are the opposite of insulators. So these would be things that are at the top of that triboelectric series. These are materials that allow electrons to flow really easily. Metals, definitely, and also some metalloids. So you see some examples of both types of materials here. All right, lastly, resistance. Resistance is the measure of how difficult it is to push the charges along. And this is due to friction. So just like when you deal with friction in everyday life, you know that when there is friction, there's heat involved. So oftentimes when there is resistance in electrical circuits, we can feel the heat coming from it. We do this with our computers and our cars. We can tell when they are aging and not working quite as well. Insulators help protect us because they resist the flow, which is one reason why they surround most electrical circuits or our wiring. Remember that with the greater the resistance, that means that there will be less electrical current, so less electrons flowing past a point at any given second. And this means that there is wasted energy, and what we have called earlier in the year dissipated energy. Both thinner and longer wires have more resistance for electrons to flow. Lastly, when you are measuring resistance, we measure in the unit of ohms. All right, I hope this was a helpful foundation